With the speaker today, Professor Bruce Twarog, who is a member of the Department of Physics and Astronomy at the University of Kansas. And so we've been colleagues for a long time. He received his PhD in astronomy from Yale University, and then he came to the University of Kansas way back in 1982. If he likes, he can tell you a little more about his career leading up to the university. But he'll talk today about the search for extraterrestrial planets. Bruce, it does help to talk directly into the microphone.
I'll be walking
around. Well, you kind of need to do it because we have a lot of old.
Mic so we can hear you good?
Can you hear me? Fine, I don't need the mic. I don't like to use mics because I tend to wander around when I talk. So if I do say something you can't hear me, I'll come by
and shot in my
ear. Your ear. You got it, that's right.
Did you miss your calling?
What would that be?
You've been a preacher.
No. My students might disagree with you, but that's a different story. Okay.
John Brown.
When you're an astronomer and you meet people for the first time, my wife is also on the faculty here, she's also an astronomer. And people ask you what you do, and you tell them you're an astronomer. The universal response to people is, wow, that's interesting. And then they sort of, you can see their minds sort of turning over, because the next question they really want to ask is, what do you do for a living? But most of the time they're honest enough to skip over that one and start going to the two big topics they always want to talk about. There's usually a third. The third one is the one which has been in the news that last month, and they're all excited about it. The big topic for the last 6 months in astronomy has been, anybody?
Dark matter?
No.
Dark energy?
No.
New planet?
No. Gravitational waves.
What?
Everybody asks about gravitational waves, right? Because they've been detected for the first time in history last year. But once you get past that sort of in the news topic, which is out there right now, there's always two big ones that come up. The first one is always...
How big is the universe?
No. I never run into you at an airport, that's good. The first thing I always ask about is black holes. Because everybody likes to talk about black holes. The second question they always ask about is this one. You turn this on.
Aliens.
Aliens, you got it. Here's the question. Are we alone in the universe? Is there anybody else out there?
Is there?
So, there are lots of ways of trying to answer the question, trying to figure out what the answer is. One, you can sit here and wait until they show up on your front lawn. That's kind of tedious, but in some ways it's a good thing, because if they do show up on your front lawn, chances are you're in trouble, and that's not a good thing. So other than having them come here, the second way to answer the question is to go after them. Let's build a spacecraft and explore the galaxy and find all the places where there is life. Now, this is a prelude to the actual talk, but the problem with that picture is the following. Here's the sun. All right? Scaled down. Even right color, it's good. All right? Here's the sun. On this scale, where this is the sun, how big is the solar system going out to where Pluto is? Anybody know? This scale, here's the sun. Where would Pluto be, roughly? No, not that far. It's not that bad, actually.
Outside this room.
Outside this room, it's about 100 meters away. So about the length of a football field. All right? But here's the point. The fastest moving spacecraft we've ever created, which was New Horizons. New Horizons flew from Earth to Pluto. It took 7 years. So on a scale of 100 yards, you're going to go 100 yards every 7 years. Next question. On this scale, where's the nearest star? Anybody know, roughly?
It's 4
Come.
light years.
Further.
Yeah, what? Anybody really know how far away the star would be? Cincinnati. Okay? So, you're going to build a spacecraft, best one we have available today. It's going to travel the rate of 100 yards every 7 years. It's going to take a hell of a long time to get to Cincinnati. All right? And there's no hope anytime in the near future that's going to change. The technology is not going to change dramatically. So going out and trying to find life yourself by searching all these other planets is not going to fly. Right? Third way, you try to find places out there which might have planets, which might have life, and study them from where we are. And the hope that you can find sub-signature by studying that planet that there's life on it. I can't get there, but maybe I can infer there's going to be life on this planet because it has a rich oxygen atmosphere, for example. Okay? So the big question now becomes, how do I figure out of the 100 billion stars I can observe in the galaxy, which ones to spend my money and time studying to look for the planets, to look for the life? This is not an easy question, but this is the big question, all right? How do I find the planets out there which I might want to study because they have life on them? So it comes down to, how do you find planets? First way most people think of is imaging. You go out, you find a big telescope, you point it at a star, you take a picture of that star, and if you get a really, really good resolution, I can see the planets going around the star. Now the hard part about this is the following. An example of our solar system. Sun, Jupiter. Biggest planet in the solar system, the brightest planet in the solar system. But if I go to another solar system which has a star like ours, a planet the size of Jupiter, how do they compare in brightness? Not from where we are, but from where they are. The answer is, Jupiter is now 1 billion times fainter than the star. So you hold up this planet and you put a light source 1 billion times brighter next to it. Your chance of seeing the star and the planet separately is 0. You're not going to see it. All right? Now, part of this comes about because when you look at the planet, you're seeing reflected light. When you see Jupiter in the sky, it reflects the light of the sun. All right? There is a way to actually see planets directly, because planets, like everything else in this room, you, the table, the walls, put out their own light. They glow because of their temperature. The problem you have is I turn off all the lights, I pull down all the shades. It looks dark because the kind of light you're putting out is not light I can detect with my eyes. It's in the infrared and the radio. I can't see that. So we see things, we see it by reflected light, but other objects put out light at long wavelengths. If I have a camera which can see things at long wavelengths, the object looks brighter than it did before. An example. This is actually an image taken back about 10 years ago with a ground-based telescope. This is on Earth, on the ground, taking a picture of this star. That's the star. It's not really a star. I cheated. This is a thing called a brown dwarf. It's called a brown dwarf because it's so small in mass, it doesn't have nuclear fusion. So it's not massive enough to burn energy and maintain its radiation that way. But it's still called a star in some crude sense of the term. You take the image, and over here you see this thing. That's actually a planet. It's 5 times the mass of Jupiter. and you're seeing it because you've taken this picture in infrared light. I don't have to see the planet by reflected light. I see it because it's glowing. And because this one is relatively low brightness, and this one is higher brightness, I can see them as two objects. This is the first planet ever observed directly outside of our solar system. But this is a tough way to do it, because the only ones you're going to find are ones like this. Really low mass objects, not the sun, and really high mass planets. And once you get beyond a certain distance, they're so close to each other, this is hopeless. So this is not going to work. Okay. Next, how do I find that there's a planet out there? I'm going to explain some basic physics. I'm going to throw a lot at you. If you don't understand it, ask Bob. Bob knows everything.
That's why we have him here.
That's right, that's right. Planetary detection 1. There are 3 techniques we're going to talk about. This is the first one. How do I know a star has a planet around it? A schematic diagram, to put it mildly. Right. Here's a star. Here's a planet going around it. This is actually supposed to be a binary system with 2 stars. Don't worry about it. Here's a star with a planet going around it. That's the way you tend to think of it. You see a picture of our solar system. Here's the sun, and the planets go around like this. The reality is, that's not what happens. Physically, it looks like this. Both objects are moving. They both have to move. It's the laws of mechanics. Newton came up with this in the 17th century. They can't be one stationary and one moving. It's not going to happen. And the reason you think about it makes all the sense in the world. This planet's moving because the star's pulling on it through gravity. But at the same time, I can make the claim the planet's pulling on the star through gravity. So if the star makes the planet move, the planet has to make the star move. The point it moves around is the thing called the center of mass. It's the pivot point, the balance point. All right? Now again, if I say something you don't understand, or I say something you don't like, stop me and ask me a question. I have no problem with that. Yes, go for it.
Why is there gravity?
Oh, Lord. There's always one in the audience. I don't know why.
Where does God come from?
Same place gravity does, as far as I can tell.
Exposed.
Yeah.
That's enough.
You missed that class.
Yes. I was absent that day. All right. So the question becomes, how can I use this? This has been used for a long time to try to find binary stars, 2 stars going around each other. And the reason is, in a binary star system, the 2 objects are about the same mass. They're comparable to each other. So I want to try to find the pivot point. The balance point is about halfway between the 2 of them. So they're both moving about the same distance around the center of mass. All right? So you find a binary system. Here's what we're looking for. Imagine, here's your binary system. I got a star here and a star here. They go around the center of mass. Go around the center of mass like this. All right? One going this way, the other going that. Now the thing is, when the stars move, they move through the sky in straight lines on top of going around each other. So imagine I've got a flaming baton. Remember the Texas cheerleaders back in the 60s? They used to have those? Yeah, the twins. Yeah. Flame here, flame here. They're going around each other like this, but at the same time, the entire system is moving through space in a straight line like this. It's going through the sky like that. So if you follow the flame here and the flame here, you're going to make a path. Both stars are not moving in straight lines. And here's the schematic. One star goes this way, one star goes that way, they oscillate back and forth across the sky. Which means if you go out and you monitor these stars over 10, 20, 30 years, you find their positions relative to the fixed stars. The background stars supposedly aren't moving. And you plot them. I can tell you the mass of the 2 stars. I can tell you there are 2 stars here because I see 2 stars, but more important, the relative masses can be determined. Because the heavier it is, the closer it is to the center of mass. If I've got a bar with a 20-pound weight and a 1-pound weight over here, where do I put my finger to hold it up? The answer is over here next to the 20-pound weight. The more massive object always makes a smaller orbit. It's a low mass object. Everybody with me?
Why do you, with the assumption about the other stars being fixed? That's not true, is it?
Aren't they
It is,
too?
on average, and that's all you care about. In a statistical sense, you'll make the claim that these stars aren't moving. Yeah.
Got it.
Right, they do have some motion, just not enough to
I
measure.
got it.
Got it. Okay, a real star. Sirius, brightest star in the sky. It's a binary. You can't see that with your naked eye because the second star is so intrinsically faint, it gets washed out by the one bright visible star. But if you have really good equipment, and you observe Sirius over about a 20-year period, here's what happens. Sirius A, the one you can really see easily, wobbles back and forth like this. Sirius B, which is a white dwarf, a low mass, low luminosity star, goes that way. And I can tell there are two objects there because they're wobbling back and forth. All right? Here's the question though. Let's take away Sirius B, the white dwarf, which is about half the mass of Sirius A, and put a planet there. The mass of the planet is 1/10 the mass of the sun. How much wobble am I going to cause? A hell of a lot less than that.
Oh, yeah.
All right? Because I got a really light thing over here, a really heavy thing over here, the center of mass is going to be almost inside the other star. So as it goes around, that star will move, no problem, but the change is so small you can't measure it. All right? The sun does this. Our sun moves about a little center of mass for all the planets. So trying to do this for a planet relative to a star, I can monitor the star and see if it wobbles back and forth, but chances are, unless you've got really high quality technology, the change in position is so small you can't measure it. People have tried for years. I heard Bob talking earlier about Barnard star. Back in the 50s and 60s, people tried to do this, and claims were made that they had found a planet around Barnard star because the star appeared to wobble back and forth. This is taken using photographic plates, glass plates with emulsions on them. All right? It turned out mostly what they were measuring was problems with their equipment, which oscillated over time. That was it. There was no real measurement, no motion. So while this should work, your detectability is almost zero because the motion is so small. Okay? All right. Where's my mouse? Here we go. Planetary detection 2. The first way, here's the second way. You're going to think this is almost the same problem, almost the same thing. It's not.
Yeah.
All right? Here we have a star with a planet going around it. Notice you're seeing the motion of both relative to the center of mass. The star actually moves in a little orbit, the planet moves in a big orbit. Which one's more massive? Question number 1, Physics 111.
Which one's what?
More massive.
The one in the middle.
One in the middle.
Yeah.
Because it makes a small orbit. The one out here, the light one, is further away from the center of mass. It makes a big orbit. So just by looking at the picture, you can tell big one, small one. How can I use this to find out there's a planet around the star? If I can't see that because it's too faint, how can I detect its existence by looking at the other star? The answer is, look at what the star is doing. If I see the orbit exactly edge on, the star is coming toward you, going away from you. Coming toward you, going away from you. It's making an orbit like this. The last time we talked about stars going like this, across the sky. Now we're talking about it seeing edge on, toward you, away from you, toward you, away from you. What you'd see, in this case, is a thing called the Doppler effect. The same way if you get caught speeding on the highway, the cop pulls out a little gun and says, you're doing 75, I caught you. The same principle applies to the stars. They emit light, and if they're stationary, you know what the light's supposed to look like. You take their spectrum. Now, if I take that star and I move it toward you at some speed, the entire spectrum will shift. If they're coming toward you, the wavelengths get compressed. If it's going away from you, the wavelengths get stretched. All right? An example. Sound waves. If I didn't break it. Yeah.
Be careful.
We got that? It's really ugly, isn't it? All right? You hear the sound? And now take it and I spin this around. As it spins around, you'll hear the pitch change. Coming toward you versus going away from you, the sound will change in wavelength, in frequency. All right? And again, because it's coming toward you, the waves are compressed, higher frequency. They go away from you, they're stretched, lower frequency. The common example most people see in textbooks is a train coming down the train tracks.
Right.
Ooh, as it goes past you. Same principle. You can do the same thing with light. Every particle of light emitted by this object is going to be compressed. No change. Expanded. No change. It's going this way. Now toward you or away from you, no change whatsoever. I can only measure the speed along the line of sight to the object. All right? Beautiful. All I got to do now is, even if I can't see this one, I can see that one. I'll take its spectrum, and over time, I will measure its motion. As the lines go back and forth in the spectrum, toward me, away from me, toward me, away from me. Here's what it looks like. Again, don't worry about understanding the picture beyond the gross outline. In this slide, the observer's over here. You're the green dot, looking this way. The orbital plane is in the plane of the board, so you're looking straight across the plane. You take the spectrum of, in this case, you can see two stars. Here are the lines. Notice these lines are going back and forth like this. And they're always opposite to each other. One star is going away, the other one's going toward you. So in the spectrum, I can see that orbital motion by seeing the lines go back and forth like this. The one line in the middle is a reference point. It's not really in the spectrum. Okay? Take away one of the two stars. So I can't see the lines. I can't see its spectrum. The other star is still there. The other star is still moving toward you and away from you. So what you want to do is look for a single star, as far as you're concerned, take its spectrum, and see if its lines are going back and forth like this over time. The lines are going back and forth like this over time. It's orbiting something. You just don't know what because you can't see it. Are you with me so far? Good.
I'm lost in space.
Just don't try to go through the center of the planet, that's all. All right, so here's our picture. It turns out this technique was actually the one which found the first planet outside the solar system. All right, here's the plot. This is 51 Pegasus. This is the plot of the velocity. The motion of the star toward you is a negative number. I'm sorry. The motion of the star toward you is a positive number, away from you is negative. So they go out and they measure the star, you measure its speed today. The next day, and next day, and next day, and next day. And you do it over and over again, and you put together the plot. What the plot is showing you, here's velocity. At this point, it's going